Hello, welcome to the second video of episode 2 of abstract interpretation. In the last videos, we proved that abstract interpretation is sound whatever be the order in which we compute abstract values for control points. However, when we have infinite height domains, the fixed points we get can be different with respect to this order. And we can also design strategies to locally improve precision. That's the object of the following section. First, François Bourdoncle in 1992 proposed a strategy based on the shape of the control flow graph. The strategy consists in computing the abstract value in the order of the program, but loop per loop. The essential notion here is the notion of strongly connected subcomponents, which we can compute by a graph traversal. The strategy then consists in iterating in each strongly connected subcomponent, converging, and then propagate before going to the next connected subcomponent and continue. It has been experimentally shown that this strategy really works in practice. You get better fixed points. Now that we have improved the global order of evaluation, let's come to a strategy that enables to recover precision after convergence. In this program, an interval abstract interpretation has been made, and we finally obtained the red invariance. However, we might need a more precise invariant at that point, at the beginning of the loop. For that, we can redo one or several iterations without widening. And each of the new invariants you get by making such step is guaranteed to be less or equal the initial invariance. Moreover, this is guaranteed to be sound. This is called descending sequence. The descending sequence is implemented with making these abstract iterations without widening and after k application, or at the first step you get an inductive invariant. We already saw in the last video that widening operators are one of the major elements that induce loss of precision. A simple idea would be to delay its application after a certain amount of steps, which is similar to angle loops. This is called delayed widening. You fix a k and you compute without making widenings for the first k steps, and then you use the regular fixed point iteration. In this example with polyhedra, I will show that delaying widening can really improve precision. So what I claim is that if I make this analysis once, and here I depict the polyhedra for P. If I make this analysis once, if I do not delay the widening, I will finally get this blue triangle at the end. However, if I delay the widening once, I will finally get this red invariant at the end. This exercise is left to the reader. We can also improve the whole design of widening operators, for instance, with adding additional information coming from the program. Here, the idea is to gather all numerical tests of the program and put them in a pool of constraints. Then, while you apply the widening operator, you intersect the result with the constraints that are both satisfied by P and Q. This is proved to be safe, and this is experimentally cool, and it was experimentally proved that in average you gain precision with this new widening operator. However, be careful, because widening is not monotone. Improving locally, which means getting a better fixed point locally, doesn't mean that your analysis will globally be more precise. Because an abstract interpretation course should last a semester, in my opinion, There are plenty of other techniques I didn't mention, apart from the numerical or non-numerical abstract domain that exists, and are several. You can, of course, combine domains in order to get better precision, and there is also a framework to make analyses that are able to change domain on the fly. You can invent plenty of other clever iteration strategies that improve locally or globally the precision of your own analysis. This is still active research after 40 years. Finally, let's come to applications. We already saw that abstract interpretation can be used to prove memory safety. In the same way than liveness, it can also prove that some part of the code can be eliminated. We prove that this part is unreachable, and then we can eliminate it. It can also be used inside compilers in order to detect vectorization optimization or memory optimizations. It can also pre-compute preconditions for given optimization to be safe, and also be used to prove termination. Now that we come to the end of the video, I will try to advertise a bit the tools that you can use to design your own abstract domains or your own abstract interpreters, or more generally, to design program analysis for imperative code. We already saw in the intro the industrial success story of Astray and Infer. I had Polyspace, which is a French success story. And I come to other tools that you can really use in practice. In this slide, I make a non-exhaustive listing of tools that you can rely on, and I let you have a look if you're interested. Let's come to more advertisement. There is a free abstract interpreter that was designed in Grenoble, and I will make a demo of it. For the demo, I already wrote inside a .txt file the example I want to analyze. First of all, I emit the LLVM bytecode for this C file, and I invoke the tool on this PC file. The output of the tool is, as expected, the very same C file where invariants have been computed and assertion checked. Here, the relational invariants have been computed for this control point, which is the head of the loop, and the two assertions which are relationals have also been proven. Now that we have made the demo, I give you the final result on this slide. Now, this is the real end. I hope that I convince you that abstract interpretation is a nice test framework for program analysis, and especially because it comes with numerous and expressive abstract domains that have been designed in the last 40 years. Tools exist. Use them for your own purpose. Propose abstract domain. Use other applications. I thank you for your attention. Bye-bye.